Hello everyone, in this video I'm going to be looking at something called the temperature coefficient. Now this is a value that you can calculate to work out the effect of a 10 degrees Celsius rise in temperature on the rate of any chemical reaction. It's really useful because then if you're changing the temperature, you can see what 10 degree jump kind of gives you the most significant difference in terms of the rate. And it's using this formula that I've got down on the screen, and it's something called Q10. So the temperature coefficient, or Q10, this is what we refer to, is the rate of the reaction at a higher temperature divided by the rate of reaction at the lower temperature. So let's think of an example, and then we'll see how Q10 is actually calculated. So many experiments that use Q10 are enzyme-based ones in school. So we're going to pretend that I have investigated the rate at which an enzyme, let's say amylase, saliva amylase found in the mouth, digests starch solution, and we're going to use 6 different temperatures. So we're going to see the rate at which this enzyme works and breaks down starch at 6 different temperatures. I'm going to time how long it takes for the same mass of starch to be digested at each temperature, and then work out the rate of reaction. So let's just quickly put some rough figures in. So let's say we've got our temperature here, and we're going to measure that in degrees Celsius. Let's say we've got time taken for starch to be digested, and let's say that our time is in minutes. So just going to view rough column headings here, and let's put in some numbers. So we might need to shrink this a little bit. Let's put in some rough numbers and then work out this Q10 and what it actually shows. So let's say we've done 10, 20, 30, 40, let's just go to 50. Let's imagine that the time taken for starch to be digested starts out at 5, then we get maybe 1.7, so 5.0, 1.7, 1.2, 1.0, 2.0. Notice we've had to put the point zeros in. It's good standard practice to be consistent in terms of decimal places. So if we were to draw a graph of this, and again, this is a very, very rough sketch. If we imagine we had temperature on the bottom and time taken for starch to be digested up the side, you might get something a little bit like I don't know, maybe this. But the key for Q10 is working out the rate. So we're going to need another column. We're going to need another column over on the right hand side for the rate of digestion. Because Q10, to work out Q10, we need values for rate. And our rate of digestion, whenever you work out the rate, it's always 1 over something. So in this case, it's going to be, in terms of our units, 1 divided by minutes. That's going to be our sort of arbitrary units in this example. So let's look at the rate of digestion. If we calculate the rate of digestion for these values that we have, 1 divided by 5, that would give 0.2. Then if we did 1 divided by the 1.7, that would give out a value of 0.59. And then we'll just finish just for completeness sake. So 1 divided by 1.2 would give us a value of 0.83. That's rounded to 2 decimal places. So we'll just work this through as an example. 1 divided by 1 quite clearly is 1.0. I should really have written 0.20 to keep the decimals consistent, but I'm not able to fit it on this screen. And then 1 divided by 2 is 0.50. So there are our rate values. So if we want to work out the temperature coefficient, we need to look at these values in blue. So Q10, so we're looking at this bit here. Q10, our temperature coefficient says we look at the rate of reaction at the higher temperature divided by the rate of reaction at the lower. So if we want to, let's start with this 10 to 20 degree jump, this first 10 degrees. Because the whole point of this is we look at the effect of a 10 degree rise on the rate of a chemical reaction. So we've gone up from 10 to 20 degrees Celsius, we've got a 10 degree rise. Now the rate at the higher temperature, which would be 20, is this. And the rate of reaction at the lower temperature would be the number in red, this one. So we're not looking at the middle column, we're looking at the last column. So for 10 to 20 degrees, so for 10 to 20, the rate of the higher temperature, which is 20, is 0.59. Divide that by 0.2, the rate, or 2.0, the rate of reaction of the lower temperature, and what you get is a value of approximately 2.95. And that's your Q10 for between 10 and 20 degrees. Now, on its own, that doesn't really mean anything. So what you need to do then is go back and calculate the Q10 for every jump. So let's just work out the next Q10, then it will be easy to see the point of doing these. So let's do the jump from 20 to 30 degrees. Rate of reaction at the higher temperature, so let's look at 30, and we'll see if we go across. We're looking at this value here, so 0.83. That's the rate of digestion, or the rate of the reaction at that higher temperature, so 0.83. Divided by the rate of the lower, or rate of reaction at the lower temperature, which is at 20, so that would be 0.59. 0.59, rate of reaction at the lower of the temperatures I'm testing for. And that number would come out as 1.41. Now, the whole purpose of Q10 is to see how a 10 degree rise in temperature affects that rate. So clearly, looking at these two numbers, here and here, this is how it works. The bigger the Q10, the bigger sort of the impact. So going from 10 to 20 degrees has a larger impact on this reaction than going from 20 to 30. And that's it. All you have to do is just look at these Q10 values. And the bigger the Q10, the bigger that temperature coefficient, the bigger the impact of that 10 degree rise. And you can keep going into the example. You could do from 30 to 40, in which case you do the 1 divided by 0.83 in terms of the rate. You could do the difference between 40 and 50, and you can compare all of those 10 degree jumps. Now, usually, as a rule of thumb, the rate of a chemical reaction, typically we say that it doubles for every 10 degree rise in temperature. But for enzyme catalyzed reactions, this often isn't the case. And it certainly isn't the case in this particular reaction that I'm describing in this video. But that's how you work out the temperature coefficient, or what is known as Q10, using the equation rate of reaction at higher temperature divided by the rate of reaction at the lower temperature. Okay, hope that helps.